So if you look at number 3, here's the answers for A. So they give you the function f and the function g. And then they tell you with the function f and the function g that they gave you to do f plus g of 2. So here's the function f and g, and I found f of 2 and I found g of 2. So here's me plugging 2 in for f. Here's me plugging 2 in for g. And then I just added those two numbers together. So I got 2 when I found f of 2. I got 8 when I found g of 2. And then I added those two numbers together and got 10. Then they tell you to find f minus g if you plug in -1. So I plugged in -1 for f and I got 2. I plugged in -1 for g and I got 11. 2 minus 11 is -9. Then they tell you to do f times g if you plug in 1/2. So when I plugged in 1/2 for f, I got -1/4. When I plugged in 1/2 for g, I got 47/4. And when you multiply those together, you get -47/16. And then if you do f divided by g, plugging in 0, I did f of 0 and got 0, g of 0 and got 12, and 0 divided by 12 is 0. So for each of these, it's basically, there's like 16 problems in here. Number 3 is 16 problems. Number 4 is also 16 problems in one. So now going back and looking at that, does that make sense now? How to do that? Okay. So we're going to be doing that for those problems. Are there any specific parts of that that we need to look at? C, 4C might have been kind of tricky. Should we go over 4C? Adding two fractions together, subtracting two fractions, multiplying two fractions, dividing two fractions. How did we do with that? Should we look at those? Sure. So for number 4, our f of x is x over 2. Our g of x is 2 over x. And for a, they're asking us to add them together. So we have to do x over 2 plus 2 over x. And right now, those two fractions are not ready to add together because when you add two fractions, they have to have the same denominator. So what would the common denominator be if one denominator is 2 and the other denominator is x? Yeah, 2x. So the first one, how are we going to make this one have a denominator of 2x? I'm going to multiply by x on the top and the bottom. So I'm going to multiply by x, multiply by x. How am I going to make the second fraction have a denominator of 2x? I'm going to multiply by 2 on the top and the bottom. So times 2 times 2. Okay, so now my first fraction is x squared over 2x. My second fraction is 4 over 2x. And now I can go ahead and write it as one fraction with a common denominator. So the common denominator is 2x, and I've got x squared plus 4. So that's what I get when I add the fractions together. Does that make sense? Okay. Part B says that you're subtracting them. So f of x minus g of x, x over 2 minus 2 over x. Similar problem. We still have to get that common denominator. So we're going to end up having x squared over 2x minus 4 over 2x. And so we're going to have x squared minus 4 over 2x. For part C, we have to multiply these together. So x divided by 2 times 2 divided by x. And what happens when you multiply them together? And Delana, go ahead and put your earbuds in prison for me. What happens when you multiply these together? Divide by 2 and times 2, what happens with that? They cancel, the 2's cancel. What happens with the x's? They cancel, divide by x and multiply by x, those cancel. And when everything cancels, what do you get? You get 1. You don't get 0, you get 1. So this is just 1. X over 2 times 2 over x. If you multiplied that instead of canceling things, you would get 2x on the top and 2x on the bottom. And we know that anything divided by itself is just 1. So 2x over 2x is just 1. For D, we have to divide f of x divided by g of x. So f of x, x over 2, divided by g of x, 2 over x. And when we divide fractions, we can do keep it, change it, flip it. Does that sound familiar to anyone? Keep it, change it, flip it. So you keep the top fraction the same, x over 2. You change it to a multiplication problem, and you flip the second fraction up to the top. So if instead of being 2 over x, it would be x over 2. So we would have x over 2 times x over 2. And when you multiply the tops, what do you get? And when you multiply the bottoms, what do you get? 4. So add them, subtract them, multiply them, divide. Those are your answers. Okay. The other problems are a lot easier. A is a bit easier because, you're just kind of multiplying a quadratic and something linear. So we've added those and subtracted those and multiplied those and divided those before. Same thing with B. D is not going to be too bad because you can't really do anything with it. So when you add it, you're just going to be like, I'm going to put a plus sign in between them and then I stop. Not a whole lot I can do. I put a minus sign in between them and then I stop. When I multiply them, I write them right next to each other and then I stop. So there's not a whole lot you can do as far as part D. Okay. Any other questions for number 3 or number 4? We're okay with those? Okay. All right. So we're going to go ahead and move along to taking notes for today. So go ahead and put those off to the side. And I'm going to hand out the notes for today. So these will be due tomorrow. Both pages, all of the work that goes with them. So just make sure you don't lose any of your work. And we'll get those finished up. Or if you've seen it, you've only seen it in a limited way. And that new operation is called composition. So composition is going to be new to us, but not terribly difficult, just new, just a little bit different. So what is composition? Composition when one function is plugged into another function. One function is plugged into another function. So there are 2 ways you can see this written. You can see f of g of x. So this notation, this means that g of x is being plugged into f of x. And the way that you read this out loud is you say f of g of x. F of g of x. F of g of x. So that means that g of x is being plugged into f of x. And then people got tired, I don't know, of writing all of those parentheses. And so a way that they shorthand that is they write f of g of x. F of g of x. So it sounds the same when you read it out loud, but it looks completely different. F of g of x. And then some people just say fog because it looks like the word fog. So f of g of x. So all you have to remember is that when you see it this way, g of x is the function that's inside. It's the one that's being plugged into the other function. Okay? I would say that this notation is maybe a little bit more common than this notation. You'll probably see this one a little bit more often. Okay, so g of x is the one that's inside. F of x is the one it's being plugged into. So what we're going to do first is we're just going to look at evaluating composition, which means we're going to look at what happens when you have all numbers, when you're taking the numbers from one, plugging them into the other. So this is pretty simple, and you guys have probably done this before, you just didn't know that's what you were doing. So if it says fog, -5, or f of g of -5, this is saying f of g of -5. And order of operations tells us that we do the inside of parentheses first, which means that the inside of the parentheses are this part. So we have to look at the inside function first. So what we're going to do is we're going to figure out what g of -5 is. It's 1, so g of -5 is 1. And then I'm going to take that 1 and I'm just going to plug it in here for g of -5. So g of -5 is 1, so I'm going to replace that. And then I'm going to do the resulting function. So now I have f of 1, which is, oh, I didn't fix that very well. There is, which is undefined. All right. Let's try the next one. G of h of -6. We're going to do the inside first. What is h of -6? -3. So this is -3, which means that next we're finding g of -3. What is g of -3? -5. Okay, this one, it says f of f. That means you're taking the function and you're plugging it into itself. So f of f, f of itself. So we're going to find f of 0, which is what? 6. Okay, so f of 0 is 6. And now we're going to do f of 6, which is -4. Okay, this one has 3. So this one is g of g of g of -1, which means that you're plugging the function into itself and then plugging that into itself. You're doing it multiple times. So we're going to say this is g of g of g of -1. And when we do this, hold on, I have to make sure my parentheses are right. That, and then I think I got them. Okay, so we start from the inside. So this, what is g of -1? So this is -5. Okay, so now I have g of -5. And what is this? 1, okay. And then what is g of 1? 7. Okay, so this equals 7. So whenever you're evaluating, you just start with the inside and you work your way out. Does that make sense? Are we okay with that? The notation is funky, but we just start with the inside, we work our way out. Okay, this one, h of f of -1. So we're going to start with the inside. What is f of -1? Negative 7, okay. And then what is h of negative 7? H of negative 7 is negative 1. Okay? And then f of h of negative 1, what is h of negative 1? 4. And then f of 4 is undefined. It's not there. Undefined. Okay. Do we feel comfortable with those? We can do those? Okay, so now we're going to take our sheet that is double-sided. And from that, we are going to work on, you can do 5, 6, and 7 from that. 5, 6, and 7 from that. And then once I give you guys a little bit of time to work, then we're going to come back to the notes and we're going to do a little bit more notes. But for now, you can do most of the back of that worksheet. Sound good? Okay. And then if you didn't have time to finish the stuff from yesterday, or if you were confused on 3 and 4, then any extra time you have, you can work on 3 and 4. Okay? I am not planning on giving you guys another worksheet today. All that we were doing is working on this worksheet today. Okay? And if you didn't have time to finish the drawing from yesterday, you can also work on that if you want to. Okay? All right. The instructions are telling us to find each composite function, and there's 2 different ways to compose the functions. You can take G and plug it into F, and you can take F and plug it into G, and we're going to do it both ways. So I'm just going to divide my space into 2. So here I'm going to take G and plug it into F. And here, I'm going to take F and plug it into G. So if I'm going to put G inside, that means that I'm going to write F out. And when I write F out, I'm not going to write the X down. I'm just going to leave space where the X was. So I'm going to say 2. I'm going to leave space where the X was, minus 3. And where the X was, I'm going to put the G of X inside. So f of X is 2 times X minus 3. Does that make sense? We can see how f of X was written. For G of X, this one was X plus 1, so I'm going to leave some space, plus 1. This was X plus 1. And inside, I'm going to be putting f of X. F of X plus 1. So now I can actually do my plugging in. So for this one, I'm going to have 2, and then I'm multiplying by the function that was G of X, and I'm subtracting 3 off the end. The function that was G of X was just X plus 1, so I'm sticking an X plus 1 inside. This part over here, you can carry it down if you want to. You don't have to. It's just notation. It's just saying this is the problem that I did. So if you want to leave it at the top and not write it in your final answer, that's okay. Or if you want to keep writing it down for each step, that's fine too. Over here, we have f of x plus 1. So I'm going to say f of x plus 1. And then in the parentheses, I'm going to plug in my f of x. I always use parentheses because sometimes you might have like this situation where it's 2 times x and then you have a number to distribute into the parentheses. Maybe in the problem it was like an x squared. So sometimes you have an operation that you have to do to the parentheses. In this case, the parentheses don't really need to be there, but it's always good to put them just in case. So over here, we're going to go ahead and distribute the 2. And we get 2x plus 1 minus 3. And so you're close. 2x. Oh, 2 plus 2. Sorry, I thought you were telling me the final answer. Plus 2. Thank you. My multiplying was bad. So final answer would be 2x minus 1. Perfect. Okay, and then over here, we don't really need those parentheses, so we have 2x minus 3 plus 1, and our final answer is 2x minus 2. So when you do composition, plugging G into F, plugging F into G, you could get the same answer. You could get different answers. It depends on the problem. Okay? So this is not like addition. With addition, you could flip them around, G plus F, F plus G, no matter what, you're going to get the same answer. With multiplication, you could flip them around. F times G, G times F, it doesn't matter, you're going to get the same answer. This is a little bit more like subtraction. When you do subtraction, the order matters, right? If you do G minus F, you're going to get one answer. If you do F minus G, you're going to get a different answer. That's kind of how composition is. You plug one into one of them, you're going to get one answer. Plug the other one in, you're probably going to get a different answer. Okay, so here's our two answers. Now the other thing they're asking us to do is they're asking us to find the domain of the composite function. And we're not going to go super crazy with this. If we were in pre-calculus, we'd go into a lot of depth with this. But what we do if we're finding the domain of the composite function is we find the domain of the function that we're plugging in, because domain is the input values. Does that make sense? So we find the domain of what we're plugging in, and then we look at our final answer and we see the domain of that, and we see if it should be more limited than what we plugged in. So the function that we plugged in for this one was g of x. So let's look at g of x. G of x was the linear function x plus 1. What is the domain of a straight line? Negative infinity to infinity. Straight lines go left forever, they go right forever. Straight lines do not have any limitations. So the function that we plugged in had no limitations. So that's kind of what we're expecting as we start off the problem. When we finish the problem, we end with something that's in y equals mx plus b form. So we ended up with another straight line. And what's the domain of a straight line? Negative infinity to positive infinity. And so we ended up with a domain that is not any more limited than what we started with. So our conclusion here at the end of the problem is the domain is all real numbers, left forever, right forever, we got everything. We're good. Okay? All right, let's look at this other one. The domain of the function that we were plugging in, f of x. F of x is 2x minus 3. That's y equals mx plus b form. That's a straight line. We know that the degree of a straight line is negative infinity. Sorry, not the degree. The domain of a straight line is negative infinity to positive infinity. When we did our composition, we got 2x minus 2. That's y equals mx plus b again. That's another straight line. Again, our degree is going to stay the same. Negative infinity to positive infinity. It did not make our problem any more limited. We just got another straight line. So sometimes the domain stays really simple. In this case, it did. This was a pretty simple example to start with. Okay, we're going to try the next problem. Again, we're going to compose it both ways. So we're going to plug in G into F. We're going to plug F into G. I'm going to write the other notation this time. So I'm going to say F of G of X. All that means is that the G is being plugged into the F. And then over here, I'm going to say G of F of X. That just means that F is being plugged into G. So for this one, I'm going to start off writing the F, but I'm not going to write the X down. I'm going to say G is being plugged into the X, and then I'm subtracting the 3 off the end. So G is getting plugged into the X for this one. Over here, we're going to start with G of X, and I'm not going to write my X down. I'm going to say something's being plugged into X, and then it's X squared plus 1. And the thing that's being plugged in for my X is F of X. We good so far? Yeah? Okay. So over here, When I plug my g of x into my parentheses, I end up getting parentheses minus 3. My g of x is x squared plus 1. And if I simplify that, what do I get? X squared minus 2. Okay, so let's look at our input function. So we were plugging in g of x. G of x is x squared plus 1. Because this is x squared, this is a quadratic, so that's the U-shaped graph. What do we know about the domain of U-shaped graphs? Negative infinity to positive infinity. They have an arrow on the left side of the U. They have an arrow on the right side of the U. So the domain is all real numbers. When I finished with my composition, I ended up with another quadratic. So this is, again, it's going to be the domain of all real numbers. We were not limited with our input function, and we're not limited now that we've done the composition. So our domain is still all real numbers. Does that make sense? Okay. All right, let's try this one over here. So we wrote down g of x. We're plugging f of x in. F of x is the function x minus 3. So I've got my parentheses squared plus 1, and into my parentheses I'm plugging in x minus 3. So now I just have to be careful. How should I handle x minus 3 squared? Mathematically, how do I do that? Do I distribute? Yeah, so here we cannot distribute because of the plus sign. So if it said like 3x, then we could distribute the squared to the 3 and distribute the squared to the x, and you'd be fine. But if you have a minus in the middle and you distribute the squared, you're going to get the answer wrong. Okay, so we have to write these parentheses twice. And you have to FOIL it out. You have to multiply it out. And you'll see why as we multiply it out. If you were to distribute this, a lot of students would say this is like x squared plus 9. But as we FOIL this out, you'll see that that's actually not what you get when you multiply it. So if we start to multiply this, we get x times x is x squared. And then we get x times negative 3, which is negative 3x, and then we get negative 3 times x, which is negative 3x, and then we get negative 3 times negative 3, which is 9, and then we have the 1 on the end. So if we were to distribute the 2, we wouldn't get those middle terms. So you want to make sure that whenever you have a problem with a plus in it or a minus in it or something like that, you can't distribute your exponent. You actually have to write the parentheses that many times, and you have to multiply them out. So we've got x squared, and then what else do we have? Minus 6x plus 10. Perfect. Okay, so there's our final answer for that. Now, if we look at our input was f of x, which was x minus 3. X minus 3 is y equals mx plus b form. That's a straight line graph. What is the domain of a straight line graph? Yeah, all real numbers, negative infinity to positive infinity. So that was our input. And then over here, we ended up with a quadratic function. X squared minus 6x plus 10 is a quadratic function in the standard form. And what's the domain of a quadratic function? The U-shaped graph. Yeah, all real numbers, negative infinity to positive infinity. So nothing to worry about there. This included all numbers. This was the same amount of limitations, and so that's good. Final answer, domain is all real numbers. Okay. So far, we haven't had a domain that has been interesting. These ones have been kind of boring. Okay, let's try the next one last problem. So we have f of g of x and g of f of x. I'm going to mix my notation here, make sure we're comfortable with both. So what should I write down for f of g of x? So I got a big square root sign, and instead of writing the x, yeah, I'm going to be plugging the g of x inside of it. So I'm going to have the x, the square root, and then plugging inside of it the g of x, which is x squared plus 4. Okay. Can we square root both of these, or do we have to leave it? Can we square root both of these, or do we have to leave it? It's exactly like the last problem. If you have a plus or a minus, you can't take, because this is an exponent of 1/2. I don't know if you guys knew that, but a square root sign is actually an exponent of 1/2. So if you are trying to apply that exponent, apply the square root to terms separately, they cannot have a plus or a minus in between. Right? So with these ones, you have to leave it as it is. You cannot do anything else to the problem. It's stuck the way that it is. Does that make sense? It is stuck the way that it is. Okay. This problem is a little bit more interesting with the domain because of the square root sign. Do you guys remember what the square root sign does? How does that impact our domains? What do we have to think about? So, yeah, stuff that's underneath the square root sign has to be greater than 0. We can't have negatives under a square root sign. Can what's under a square root sign be equal to 0? Can you square root 0? Try it on your calculator. Can you square root 0? Yeah, it's just 0. Okay, so what's underneath the square root sign can equal 0, and it can be positive. Those are our two options. All right, so let's look at our input. Our input was g of x, which is x squared plus 4. That was our input. The domain of our input is what? It's a quadratic function. That's a U-shaped graph. What's the domain of a U-shaped graph? Negative infinity to positive infinity. Okay, so all real numbers is what we plugged into this function. And then once we were done with the composition, we ended up with something that had a square root in it. So now we have to look at this and we have to say, okay, we've got some stuff underneath the square root. We know that the stuff that's underneath the square root has to be positive, and it can be positive, but it could also equal 0. So the stuff that's under the square root, x squared plus 4, has to be greater than or equal to 0. We know that for sure. Okay. If you look at this, whenever we did this, if you guys remember back to that assignment when we were solving for x and we were doing the domain problems, if we tried to solve for x, can anyone see what would happen if we tried to do this? We can go ahead and do it. Let's solve for x. What should we do? Minus the 4. X squared is greater than or equal to negative 4. And then what should we do? Square root it. So we're going to have x is greater than or equal to, yeah, I mean you can, but what happens if you do? You get an imaginary answer. Are imaginary answers like actual answers? No. So there's no actual answer that would make this domain not positive. Which makes sense, right? If you have a number squared, what happens when you square a number? What types of answers do you get? You always get positive answers. So we have positive answers plus 4. are positive answers plus 4 positive. Positive answers plus 4 are positive. So what's happening here is no matter what we plug in for x, our answers are always going to be positive. Does that make sense? Our answers are always going to be positive. It doesn't matter what I plug in for x, because when that number gets squared, it's going to give me a positive result. Okay? So my domain here, the square root could have changed things, but my domain is actually still negative infinity to positive infinity, because even if I plug in a negative number, when I square it, it's going to become positive. And then a positive number plus 4 is going to be positive. So this was, it looks, our result tells us it's not very interesting, but it still like made our brains hurt a little bit to get there. Okay, let's try the next one. Take g of x, plug f of x inside. So what should I be writing? Parentheses squared plus 4, okay. And f of x goes in the parentheses. So what am I putting inside the parentheses? Square root of x, okay. Is there any simplifying to do? Yes. The squared and the square root and the squared cancel, and I just get x plus 4. Okay, so let's look at the problem. We have f of x is the square root of x, and when I have the square root of x, what was the domain? How do I find the domain of a square root problem? How do I find the domain of a square root problem? You have to think back to that domain worksheet. This is one of the ones that's limited. What's underneath the square root sign has to be positive or 0. So what's underneath the square root sign has to be greater than or equal to 0, and then you solve for x, right? This only has an x underneath the square root sign, so this is the domain. So this is the domain written as an inequality. How would I write the domain as an interval? 0 to infinity, so this says x is greater than or equal to 0, so 0 is the smallest number, infinity is the biggest number. It says it can equal 0, and you can never actually get to infinity. So these are two different ways of saying the exact same thing. Okay, now the final answer looks like a straight line. What is typically the domain of a straight line? Negative infinity to positive infinity. Okay. Would it make sense to start off saying I can only have half of the numbers in the world, and then somehow get to the end and say, oh, now I can have all the numbers in the world? Does that make sense? No. So if you start off with a limited amount of numbers, then you're going to end with a domain that is at least that limited, or it could be more limited. You can't be less limited, you can't add more numbers, but you could have less numbers than you were allowed to have to begin with. This is kind of like the rules to a game. The rules to the game are you can have 0 and anything bigger than 0. And then somebody else starts playing the game too, and they add their own rules. Their own rules can't make the game easier, they have to make the game harder. Does that make sense? So we can't say, I can only have 0 and all the positive numbers, and then this person joins the game and is like, just kidding, we get to have all the numbers in the world, including the negatives. They don't get to do that. We don't get to go back and make the game easier for everyone. We have to say, if this one says 0 and all the positive numbers, then this one has to agree. The domain is 0 and all the positive numbers, even though it doesn't quite look like that. In fact, if you actually graph this, you'll be able to see that on the graph. So I'm not going to graph x plus 4 because that was the simplified version. I'm going to graph the square root of x squared plus 4. And if I graph that, you'll be able to see that only 0 to infinity is the part of the graph that's going to be there. it looks like the linear equation with a slope of 1 and a y-intercept of 4. It just starts at 0 and it goes to the right. Does that make sense? So we start with the input domain, and then we look at what we think the output domain is, but we make sure the output domain is not less limited than the input was. Does that kind of make sense? We're going to do more of this tomorrow. I just want to make sure that we got like a little bit of an introduction today. So based off this, you're going to do number 8, and you're only going to do A and B. So C and D you're going to cross out. You're only going to do A and B. Cross out C and D. Actually, just cross out D. You can do C. I just didn't want... I'm sorry, you can do C. We did the radical one. I just don't want you guys to have to do the fraction one. Okay, yes. Yeah.